My name is Rob, and I'm going to be in charge of the last session here this evening. Title of the session is In-Network Processing and Local Algorithms. Our first speaker is Sisu, and I'm probably doing a horrible job pronouncing the name, so I apologize for all my presenters. She is at the University of Illinois, Chicago, where she's a third-year PhD student. Her research topic is distributed signal processing and computing over wireless sensor networks, and the title of the talk today is going to be Power-Efficient Algorithms for Fourier Analysis over Random Wireless Sensor Networks.
My research topic is power-efficient algorithm for Fourier analysis over random wireless sensor network. I will begin with background and problem statement to read our architecture design. This architecture basically involves fundamental of NDFT and separable to the FFT algorithm. And finally, I will use Java integrated development environment CNES1 to evaluate the final results and make a conclusion. Fourier transfer computation is the most common signal processing task for frequency analysis of sensitive data field. We are interested in the in-network distributed implementation. Its major characteristic is it combines local and global computations. It is a very ideal vehicle to study the interaction of computation and communication overhead in wireless network. Past work has presented some FFT computation, but they are based on the assumption that sensors are uniform arranged on a single line. There are two pictures here that shows the 16-point structure of FFT, one-dimensional FFT computation. However, sensors are generally not uniform equal-spaced grid arranged. In most applications, the layout is random and two-dimensional. So, existing distributed Fourier analysis solutions cannot be directly applicable for such a wireless network environment. Our work based on the network of two-dimensional topology, and it is also random deployed. We proposed a hybrid computation structure consisting of a local non-equal space DFT and a global 2D FFT. We address this problem by proposing this novel architecture. From a local perspective, non-equal space DFT is applied in a suitable choice of clusters and to get initial uniform Fourier coefficients with allowable estimation error bounds. From the global 2D FFT perspective, we proposed an energy-efficient one-dimensional FFT algorithm by using bit indexing matching strategy, which is applied to rows and columns. Let's look at the details of this architecture design. Suppose we have N sensors, and they are random distributed in a square area. We divide the whole sensor field into non-overlapping blocks of size A by A. And in each block, we choose randomly one cluster head, and the others serve as flavors. The class heads are random chosen during each time period, and are responsible for data collecting and location information broadcasting to other class heads. There's a picture shows There's an example of 500 nodes random deployed over sense network with NDFT blocks identified. As we see here, that 8 by 8 NDFT block has been divided. And after NDFT block divide, each cluster head will collect the sensor data from his label nodes and perform a local NDFT. After a local NDFT computation finished, each block is further divided into B by B subspaces, and the global FFT nodes will be chosen to represent these subspaces. Still in the same example, that 50 nodes network has been divided into 16 by 16 subspaces, and based on these subspaces, we use the 2D FFT computation method. Let's step into the details of fundamental of NDFT. The generalized discrete Fourier series for non-equal space data can be represented the Formula 1. As we see here that the frequency and time components are both non-equal space. Since we are only interested in the uniform frequency components, so we simplify the first formula into the second one, and then we perform the inverse of this formula. We got the non-equal space for a discrete transform. The basic idea behind the computing Fourier coefficients of NDFT is to find enlarged oversample data based on the given non-equal space data. During the procedure of computing NDFT, there will be two approximations. Aliasing error is caused by omitting the harmonic frequency component, and the band length size or window size will lead to truncation error. Let's look at the steps of fast computing NDFT. First, we need to choose a window function. During our actual implementation, we choose function, and we compute his Fourier series. After we choose the window function, then we expand the non-equal space data into enlarged equal space data, and then we perform the discrete Fourier transform. Then we divide it over the Fourier series of window function. With the final result can be seen as the approximate value of the Fourier coefficients of NDFT. As we see here, that step 2 actually can be viewed as integration process, which enables the local NDFT algorithm. So we use a classical linear form of integration and a generalized integration method to finish the step 2. And we also use the weighted least square approximation to fasten this computing and improve the performance. After we finish the local NDFT, we begin to perform separable two-dimensional FFT. Since 2D FFT, we know that we can perform 1D FFT around column and the row, separate rows, so we can just think about 1D FFT in the following illustration. Consider an endpoint, we proposed an energy efficient algorithm to try to save a transmission number. So consider an endpoint input with log n phases, and each node ID has a binary index representation. We also take k as the middle phase, and two groups formed depends on the binary index that is in front of or behind his bits. If in specific bit is equal to 1, then we need to do complex multiplication. We also define the permutation function in order to bring butterfly permutation partner close to each other. Q function is defined as binary index left circular shifting function. In this example, we see that in any j's phase, then we take the resting j plus 1 bit left circular shift 1 bit. So in this case, then the final binary index will become b1 to bj plus 1. We also defined p function as inverse shuffling function, which works on the binary index so that any bit bj will be replaced as bn minus j. So let's go to the detailed procedure of the global 1 DFFT implementation. In the phase 1, we only need to compute the butterfly computation on the neighboring sensors. And the Q function, the second operation we will use the Q function, works on the last 2 bits of logical ID. So in this case, the last 2 bits B2, B1 will become B1, B2. And in the phase 2, since Q function works on the binary index, so butterfly computation will still take place on the same neighboring sensors. And then the second operation still we use the Q function work on the binary index, but in this case we work on the last 3 bits. Let's look at the example. Okay, so this is an example of 16-point FFT structure. The black line represents the butterfly computation, and the right line is the function that we defined. And after the function works on the binary index, then we shuffle the data within network. So in the second phase, we see here that the butterfly computation only takes place in neighboring sensors. There is a special phase is for the middle phase K that still butterfly computation will take place on the neighboring sensors, but we use P function instead of Q function working on the binary index. So the whole binary index will be reversed. And then the second group works in the same way and until it reaches to the n-1 phase. And then finally, the logical ID will become B1 to Bn. And the additional benefit of this function is that the output will come out in a natural order. So it will save us the extra work to find the mapping points. So we do the theoretical analysis of computation number of the proposed algorithm. Since we assume that the distance between two subspaces is as unit 1, so the transmission number and the transmission distance can be interchangeable. So we use the transmission number. So we calculate his upper bound. It is proportional to n to the power of 1.5. Traditional FFT transmission number is proportional to 2 times the n to the power of 2. And there's also other paper that also tried to reduce the transmission number, but they are their upper bound is 2 times the n to the power of 1.2. So we have the transmission number, and in that case, we further save the energy. We're using DCOSS'12 as the simulator to evaluate the performance. This is a ratio of the energy consumption between our proposed architecture and the previous one. As we see here, it is all smaller than 1. So finally, we also divide the N as a signal to noise ratio, which is ratio of proposed architecture, implementation architecture compared with centralized DFT method. With the increase of network in density, we see that the performance increased significantly. And in order to further improve the result, and we also adopt a strategy of expanding the cluster head by including the data from the neighboring clusters. And we see here that SNR2 has improved greatly than SNR1. This evaluation is based on 2 distribution of data set. Okay. In a conclusion, we design a hybrid hierarchical structure consisting of local 2-dimensional NDFT computation and global separable 2D FFT computation. This architectural design advantage is that it relieves the signal from centrally computing NDFT and take full advantage of distributed computing power available within the wireless sensor network. And we also proposed the NDFT approximation performed locally, and we proposed a new algorithm try to reduce the transmission number in the global. So we plan to incorporate other network topology and approximation models in our future work. That's what I want to see for the moment.
So do we have any questions for the speaker? So I guess I have a quick one. So I understand you're investigating the FFT based upon, one of the things about it is the butterfly, and that's why you're looking at implementing it this way. Does this scheme work for other transformations, like a wavelet transformation, maybe?
It actually doesn't work for the wavelet because this algorithm aims to reduce the transmission number. Is based on butterfly structure. Yeah. So the function that we define is just work for the binary index. So it is very specific for the butterfly structure.
Okay, great. So driving more use of the FFT. Good job.
Yeah,
Thank
yeah.
you. Okay, thanks. Let's thank the speaker one more time. Okay, so our next speaker is from CEIT Spain. He is Xavier Insausti. And again, I apologize for the pronunciation. He's done also research at MIT and University of Navarra. His research interests include information theory, coding, and compression schemes. In addition, he's also interested in distributed computing and wireless sensor networks. And the title of his talk is Distributed Subspace Projection in Wireless Sensor Networks Using Computational Codes.
Good evening, everyone. Thanks, Rob, for the introduction. You pronounced my name correctly, so congratulations. But now I don't know how to. I'm going to give the next 2 presentations, so I'll try to be brief because we are all tired. We've been here since 8 in the morning. So these 2 works are related with subspace projection. So I will make only one introduction because it's kind of related, and then I think it will be faster. They are also pre-mathematical words, but I will not enter into the maths. I'm going to just give the ideas and the algorithms. I don't want to enter into the details. If anybody is interested in the deep details of the algorithms or the maths, I mean, you can contact me afterwards or by email or whatever. So in this first work, we are interested in computing the projection of a subspace. We will later explain what it means, but the key here is to improve the schemes were developed so far. And in order to do so, we will use computation coding and kind of modification of gossip algorithm. So I am first, I don't know if you hear me. So first I will talk about gossip algorithms, how things have been done so far, and still are doing, and it's okay, but we are proposing let's say an upgrade of one of these algorithms. Then I'm going to talk about subspace projection, what it's meant with subspace projection. Then I will explain our modified algorithms and why it works and why these modifications are required in order to compute projection. Then I will briefly introduce computation coding. And then I am going to give the results of analyzing these results when you are talking about, I'm writing there fundamental limits in the sense that it's an upper bound, okay? Because it's not going to be a simulation, it's just going to be an analysis, a fundamental analysis of what's the best point or what's the best thing we could ever reach with this algorithm. So I'm going to start with this very simple wireless sensor network architecture or whatever. So we have sensors in the space randomly situated. For each sensor, we define a distance d, for which we define its neighborhood. This means that each sensor can only contact the neighbors that are within this space, within the distance d, and this is because the power of each sensor is limited, pt. Then the nodes within the coverage area of each sensor form its neighborhood. And the important thing here is that every node only knows information about its neighbors. I mean, the central node in that case, doesn't know anything about the nodes outside its neighborhood, right? So everything we are going to do is very distributed in the sense that one node doesn't need to know what happens outside its neighborhood. Okay, so how do random gossip algorithms work? They are mainly used to compute averages. I mean, every sensor measures a certain magnitude and assume that the entire network wants to compute the average. So how does it work? Well, a node randomly wakes up, it contacts a neighbor, transmits its observation, then the neighbor returns the observation, and both can compute the average between their observations. So if we repeat this in time, it can be shown that the entire network will converge to the average. Okay. So there is a slight modification in order to compute the average, which was introduced by Nasser and Gaspar, I think, and it was using computation codes in order to compute the average. And it was shown that you could improve a lot the energy and time in order to compute the average in a distributed way. How it works? Well, again, a node wakes up randomly. It contacts all its neighbors, and all its neighbors using a computation code can. Then I will explain what a computation code means. But the idea is that every sensor in the neighborhood transmits its observation, and the code is designed such that the observations are added into the air, so the central node just gets the sum. Then he directly gets the average of the neighborhood, and now the last step is to broadcast this average. So in one single step, the entire neighborhood got the average of the neighborhood. It's clear if you repeat this in different neighborhoods, at the end this will converge to the average. So this is how things can be done in order to compute the average. But we are not going to compute the average, we are going to compute the projection. Now I'm going to explain what projection means here. So average is a particular projection in which you get the sum of all the observations and then divide by n. N is the number of observations. But here you have, I'm writing there, signal subspace. Imagine that the signal you are trying to measure lies in a subspace of dimension r, for instance, but you have much more sensors than the dimension of the subspace, say n. So sensors, at the end of the day, are going to measure a quantity z that is not going to be into the subspace, because noise has taken this quantity out of the subspace. So we are interested in projecting this quantity into the subspace, because that way we will reduce the amount of noise considered. Okay, so you will know from elemental algebra, we can define this operation by defining a projection matrix P. So at the end of the day, we are interested in obtaining this sheet here, which is just going to be P times Z. Okay, so if we weren't interested in doing this in a distributed way, well, that would be very easy, because at the end of the day, you have to, P times Z is just linear combinations of the elements of Z, with some weights. So it would be easy, but the problem is that we are interested in computing this in a distributed way. So what does it mean? It means that in an iterative fashion, we are going to compute or perform the following dynamics, such that every time we are going to multiply the current observation by a matrix W. This matrix W has the property that in those positions in which those two nodes are outside the neighborhood, I mean there is a zero because they cannot communicate. So this matrix W is a mapping, let's say, of the topology of the network, right? So here says the topology constraint: if two nodes are not in the same neighborhood, in that position the matrix W will have a zero, and if they are in the same neighborhood, it will not. It can, but it doesn't have to. So convergence condition means that, well, I'm not going to explain every step, but at the end of the day, when t goes to infinity, when we multiply W times W times W times W, this has to converge to the matrix P. That's the projection. We wanted to compute the projection P. And at the end of the day, in principle, there are many matrices W that satisfy previous two conditions. So we are interested in that one that minimizes the spectral radius of W minus P. Minimizing that will mean that the convergence will be as fast as possible. Okay, so computing that W matrix is at the end of the day solving a convex optimization problem, which can be done, in principle, can't be done in a distributed way, but we are going to assume that we know that matrix W, so we are given that matrix, and nodes know every node only needs to know one column of this matrix, so we are going to assume that they know. Here there are two conditions, but I'm not going to enter into that much detail. So why, in order to compute projection, is not valid the previous strategy, the previous neighborhood gossip strategy? Let's see. Imagine that node 1 wakes up and contacts its neighbors, which are node 2, 5, and 6. So imagine that she requires their observations weighted by this W coefficient. So that would be okay, that would be nice. Now node 1 would have the weighted sum of the neighbors. But the problem now, the first difference is that it cannot broadcast the observation because, of course, node 5, node 6, and node 2 are not interested in the same value because this is not the average, it's a projection. So this will be the first difference. This is not a big issue, but we have to take this into account. But there is also another problem. Now, if you see node 1 has computed the first gossip round, what we call. Now imagine that node 2 wakes up and wants to get the observations from its neighbors, which are node 1, 3, and 4. What happens? Node 1 now can't send its current observation because node 2 is in its, let's say, in its initial gossip round. So it requires the previous observation. So node 1 should send the previous observation. You can see here, right? So this is the second difference. So in order to solve that, we define a master-slave relationship between nodes and a gossip weighting state in such a way that that at the very first round, imagine that node 1 here there is an example. I will explain together with the example. Imagine that node 1 wakes up, so its relationship will be master related to the other neighbors. This means that no other neighbor will be able to wake up again until node 1 wakes up and gossips, right? So in such a way, even if it's distributed, we are setting some rules that is going to maintain the operation synchronized, so that every time, well, here I'm missing something. Now, okay, so that's what I was saying. So and then if a slave is requesting a master node an observation like here, the master should know that he has to send the previous observation and not the latest one. So with these two modifications, we have modified a neighborhood gossip algorithm, and we will see that it can compute the projection in a reasonable time. Actually, here is an example with 6 nodes, I guess. Yes, and a subspace of dimension 2. So here you get the error in terms of the gossip round, and using 2 or 3 gossip rounds, we have almost converged. So now how computation coding helps here, and why using computation codes guarantees that we are going to save energy and time. Well, computation coding is, well, here says the most energy consuming state is when all nodes in the local neighborhood transmit their corresponding observations to the central node. This could be done, I mean, if many nodes has to send their observations to the central node, it can be you send the observation first, then you know, by time division. But using computation coding, we can, in a single transmission, all the nodes can transmit their information. So here is a multiple access channel, which is the one we are considering in this work. And we are also assuming, and this is probably assuming too much, but we have to assume that for using computation coding, that nodes know the channel in their neighborhood. So under that condition, the multiple access channel behaves just as simple adder. So in that condition, we can use computation coding. What is computation coding? Well, computation codes can be designed to compute sums very efficiently and reliably. Not only sums, but here we are interested in a sum. So here is a sketch. First, all nodes in the neighborhood encode and serve their values using identical linear code books. The transmitted code words will be added on the channel, and node I will receive the sum of the code words. That's what I said at the beginning, right? So since the code book is linear, the sum of the code words is also a code word, and it actually corresponds to the desired sum. And node I has to simply add the received message to its observation, weighted by the coefficients to get its desired new observation. So this is basically how it works. Here are a couple of theorems, which I don't want you even to read, because I don't want to enter into the maths. But the basics are, here the question would be, well, and the computation code, how it works, or when it works, or which are the conditions. Well, you have there the conditions, but I'm not going to enter into that condition. I'm just going to explain the basics. And you have there, all sensors use the same lattice code. At the end of the day, it's a lattice code. The lattice code is chosen to be simultaneously a good channel and a source code. Sensors quantize their weighted observation vectors to the lattice, and they transmit simultaneously. The receiver decodes the sum and makes an estimate of it. And now, it's the key point here. Transmitters send their quantization errors, because you have a lattice, and if you want to transmit a real number, you will have a quantization error. Then first you transmit the closest point, then you quantize the error, and then you submit the error, then you transmit the error again, until, here it says the process continues until the number of channel uses is exhausted and the desired precision reached. So if the computation code is well designed, at the end of the transmissions, you will get the desired projection. So here is just a result. I'm not going to enter into the maths of how this formula rises, but this is the gain of our scheme compared to the best possible separation-based scheme. What do I mean with the best possible separation-based scheme? Well, I mean, if every node would work as a single node without cooperation, the best it could do is compress its information, or maybe use not using computation coding, not using this strategy of adding into the channel. If we compare with the best strategy, this is the gain we get, right? I'm not going to enter into the details. If anyone is interested in how this works, you can email me, or we can talk later. But here is the result. For some particular parameters, we get, this is in dBs. So you see, as the density of the sensors in the network increases, the gain increases exponentially. This actually is in dBs, well, as the network increases, this is increasing exponentially. So you see that the gain is really considerable. You also have time gains, because, as we said, when all the nodes transmit to the sensor node, you don't have to transmit every node per time, but you can, all the nodes can transmit their information at the same time. So you also get time gain. Okay, so the conclusion is just that we have used we have modified the general gossip algorithm in order to compute projection, because they were used to compute average so far. And combining computation coding with a gossip algorithm, we have get this energy and time gains. So this ends the first talk. If you have any question.
Any questions from anyone? All right, so I actually have a really quick question. If you go 2 slides back. Yeah, so here in this, one more above, yeah. So 2 more forward. Slide 17, I think, yeah. So would you or would you not expect that curve to sort of reach an upper bound as you keep adding nodes? Would that gain eventually reach an upper bound or no?
No, you are not going to get an upper bound. This will be increasing exponentially.
Okay.
You don't expect an upper bound because if the density of sensors increases, I mean, at the end of the day, you would have the region of the speed plenty of sensors. This would be something probably unrealistic. So the gain could be also unrealistic. So no, there is no upper bound. And also consider that this is a fundamental limit, which doesn't mean that it's going to be possible to get into a realistic system.
Okay, thanks.
I think there was another question.
I have a question. Maybe I not fully understand that. Since when you're doing a projection, that do you assume that all the W matrix has already been is given? Is the
Yes. In this work,
But since the matrix is exactly involved the global nodes, right? So if you initial data are given, so it's like not like realistic, right?
no, I know, and you are completely right. And now it comes my second word about this matrix, but and I will explain it. But the thing is that you are right. If this matrix is being given, if it's being calculated by using convex optimization, this means that someone knows the situation of all the nodes and knows everything, knows everything about the network.
So,
Exactly.
Yeah, so that means that Gaussian algorithm won't be like, directly applicable.
Exactly.
Yeah, it's not that complete makes sense because you have already know that everyone knows. And you don't need to use the
But you only have to know once. I mean, and not all the nodes. I mean, there is a third party that computes the matrix and then gives that matrix to the nodes. But now, because in the beginning you cannot compute the convex optimization problem of that kind in a distributed way. But we will see that you can. And now it comes my second word.
So so one more question is about, it's still the same way, it's still the same question. It just since you haven't assumed that how many times, the team, how many times that we need to do the interpolation, intonations. So we still cannot find the initialization of the matrix correctly.
I don't.
It depends the team, right?
Are you talking about?
Because you integrate the team, yeah. So formally the converges to the projection matrix, but because you didn't give the exacting number, so the initial W will be depends on that.
Yes, the convergence rate actually depends on this spectral radius of W minus P, and it can be computed for the worst case initial vector, which is, I think it's written in the paper, it's not in the slides, but yes, it can be computed, and it's, if I don't remember wrong, it's 1 over the logarithm of this spectral radius. I don't exactly remember, but yes, you're right. But here we are assuming that, the optimal matrix W is given, in the sense that this is the matrix that converges the fastest. This doesn't mean that there is always a matrix. This problem doesn't have always a solution. Depending on the network, of course, if you have two nodes here and you have the rest here and they are not connected properly, you cannot compute the projection. So depending on the topology, the problem will have one solution, will have many solutions, or will have no solution at all.
Yeah, since if the number of the nodes have been increased.
If you want, we can okay. Talk later, and because otherwise we are going to be late.
Exactly. That's good. So this sounds like a good conversation over dinner tonight. And it seems like the first question was a perfect introduction for the next talk.
Yes,
by our same presenter here.
Exactly. So I don't know how much time I have left, but okay. So exactly, thanks for your question, because now I already said what I'm going to do in my next work, in my next, here start. Okay. So the objective now is to compute that W matrix in a distributed way. I said in principle it's not possible, but it's not possible to solve the convex optimization problem as it is in a distributed way. But here I propose an heuristic approach using computational code, genetic algorithms that we will see that will get to compute that optimal matrix. So there is the objective: compute the transition matrix for the prediction problem in a distributed fashion, use gossip algorithms and a distributed genetic algorithm. So the introduction is the same. You know what I'm trying to do. And here starts the new thing. So we have here three constraints for the problem. The first constraint is the topology constraint. We already said that the matrix W has to be zero in certain positions, in those positions in which nodes are not connected. So in some way, this is, if we have to compute everything in a distributed way, nobody in the network is going to know the entire matrix. Okay, so every node will only, at most, know one of the rows or columns of this matrix. So here I am going to call Wi to every row of the matrix, and I am also removing the zeros from this row, because most of the entries will be zero, but consider only the non-zero entries. So at the end of the day, every node will have a vector of unknowns which have to solve. So the condition of the convergence, it can be shown that it is equivalent to P times W equals W times P equals P. So this is if and only if relationship. If we require, because in principle we don't have to require, but we will require that W is symmetric, because it doesn't make sense that, well, it could make sense, but we are going to assume that the transmission from one node to the other is the same from the other to the one, right? So it's enough if we solve P times W equals P and then keep always the matrix W symmetric. It's not that easy, because remember that the matrix is in a distributed way, so keeping symmetric is going to involve some problems that we will try to solve later. So at the end of the day, each node has to solve this Pi times Wi equals, this PW equals P can be solved row by row. So there's no problem by solving this locally. So the solution of this is going to be certain matrix with it. It's going to be the null space of this matrix Pi, certain degrees of freedom, and a particular solution. So this can be computed by each node without, in principle, any problem. Here, when we set all the possible values in this CI, we will get all the possible WIs, which satisfy this previous condition. And then we will have to keep the matrix symmetric, and then we have to minimize the spectral radius of W minus P. Okay? So this is what we are trying to do. Let's see how we can do it. So first, remember, when every node solves the first equation, this equation P W equals P, it gets a number of degrees of freedom, right? So the algorithm is going to consist of decreasing those degrees of freedom until a particular solution has been obtained. And besides this equation, we are going to add new equations in this form. So when a node wakes up, we'll eventually somehow, I'm trying to explain it too fast and maybe I will miss something, but every node will add an extra condition in such a way that, imagine that at the beginning there were, then I have an example and I think it will be understood more clearly, but imagine that I am a node and I have 5 degrees of freedom. So first I will impose myself one value, so I will have 4 degrees of freedom, but if I impose one value for myself, I will have to impose it to my neighbor, because you have to keep symmetric the matrix, right? So this will continue until all the degrees of freedom are gone, and at the end of the day, one matrix will be obtained. We don't know if this matrix will be good or not, but we will obtain a matrix. So this is what I'm saying there, problem of degrees of freedom and the symmetrization. This is exactly what I meant. So I'm going to show an example, and I hope it will be more clear. We have this topology, this configuration of 6 nodes. It's not the same as before. So the dotted lines means which nodes are connected with which nodes. So imagine that we have a particular solution. We solve the PW equals P, and every node gets certain degrees of freedom. So randomly, one node wakes up and sets a value for itself. So the degrees of freedom it had are decreased in one unity. But if it has set a new value, it has to transmit this value to its neighbor, right? So in principle, node 2 had 3 degrees of freedom, and now if it sets this value, will have 2 degrees of freedom. So in principle, this is finished. But now let's see what happens in this case. Node 3 wakes up, has 2 degrees of freedom, sets 1 for itself, transmits its observation to its symmetric neighbor, which is node 4. Okay, node 4 decreases its degrees of freedom, now it has 0, but assume that since it has decreased the degrees of freedom, imagine that the value it has changed affects also node 5, it could happen. So it transmits the message with an identifier to node 5 and says, well, in that position you should put a number 6. But node 5 didn't have any degrees of freedom, so it will say, no, I can't. So node 5 will send another message back to node 4. Node 4 will undo its computation, will increase again a degree of freedom, and will send back again to the first node the error message, node 3, and will again increase its degree of freedom. Let's say we have undone all the work. But now we know that the node 4 is the one that has the problem. So node 4 has to wake up now and set the value that is correct. Because if it sets a value that is not correct, it knows that from node 5 it's going to get an error. So now it can set a correct position and then transmit it to node 3, which has enough degrees of freedom. This would continue until nodes run out of degrees of freedom. So this is roughly the idea of this algorithm, right? I'm saying that there are more cases, and I'm not going to enter into all of them, but this is the most important casuistic. Okay, so let's assume that this algorithm worked and we got a tentative matrix W hat, which in principle, because of the way we construct it, we know that it will fulfill the topology constraint, and it will be P times W hat equals W hat times P equals P. This, of course, will be accomplished because of construction. But now we don't know if the spectral radius will be less than 1 or not. If it's not less than 1, this means that this matrix will never converge to P. If it's less than 1, it means that we are done. Not we are done, but at least this matrix would be valid to compute the prediction. Probably it's not the optimal, but it would be valid. In order to do that, and I'm not going to enter again into the math, I'm using the power iteration method, which means that iterating this matrix, I can compute the largest eigenvalue. So I'm not going to enter into the details, but the recursion I am going to make in the network is xk is going to be W hat minus p times xk minus 1. If I choose this for any initial x0, this would eventually lead to the largest eigenvalue. But in particular, if I choose one that is perpendicular to the subspace, such that p times x0 is 0, I will get xk equals w hat k times x0, which is, if you remember, exactly the same dynamics we got in the previous presentation. Actually, it's a projection of x0 in this subspace. So we can apply all the strategy of the previous work in order to compute the projection, and that projection will be actually the largest eigenvalue of this matrix. So even if nobody knew the entire matrix, we are able to compute one matrix, and we are able to evaluate if this matrix is good or is not good. So now this is like producing cars in a factory. We are able, if we can build one matrix, we can build many matrices, and we can use a genetic algorithm in order to improve the spectral range. So we are going to do exactly that, create many matrices and iterate until we get the optimal value. So I'm not going to explain how genetic algorithm works, but the basic steps are that, as we said, each node solves the initial equation. Nodes perform a symmetrization stage. As we said, if they put one value, the neighbor has to put the same value. Nodes evaluate the degrees of freedom. They will need this many variables, and will create a random population of some individuals for each variable. The network will generate so many W hat matrices, and will evaluate the spectral radius for each one. So here comes the distributed genetic algorithm. Each node will keep the best solutions. Well, here is, we will set also a stopping criteria, because this is an iterative process, and at some point we will have to finish. But in principle, if the finishing criteria is not fulfilled here, we continue. There is crossover, which means generate the next generation by crossing individuals. Flip some bits for mutation, and then again go to step 4, then generate again more matrices. You know that at least will be, in every step of this algorithm, you will not get worse matrices. You will at least get the best one of the previous population. So at the end of the day, you will be as close as you want from the optimal matrix. And here is an example of projection again, 6 nodes. I think it's the same topology as I showed in the example. A subspace of dimension 2, 6 nodes. The optimal matrix would be this. This is by computing using the convex optimization algorithm, the normal algorithm. We would obtain this matrix, which can be shown that is the optimum, which has 0.5 of performance. And here we see that in a single realization of this algorithm, you see, we have 80 iterations. At the very first iteration, we got a matrix that was not good, because the spectral radius was larger than 1, so it didn't converge. But at the second iteration, we already got a matrix that was valid, and you see, as the iterations increase, we are approaching to the optimal matrix. And here in the right, you have, if we repeat the experiment 200 times, I think this is the average spectral radius you get. So you see that in 2 or 3 iterations you are always below 1, and if you increase the number of iterations, you are getting closer and closer from the optimal matrix. So that's what I want to say. Do you have any question? Again.
Any questions?
So you mentioned that it's not critical to have
You mentioned it's not really critical to have W.
symmetric, or you did assume symmetric. And it seemed like when we got to the part about the degrees of freedom algorithm, it actually makes things more complicated to force W to be symmetric. So I was wondering, what would change if you just allow W to be,
Okay, if it's not symmetric, here's the problem. This condition is still valid. I mean, P times W equals W times P. Then, if W is not symmetric, you should solve W times P. I mean, the same way you solve P times W, you should solve W times P. But this cannot be done in the same way. Like, you take the first row of W and the first row of P, because nobody knows the entire matrix W. So you can't do the same strategy. So if you don't assume that W is symmetric, the problem is much more complicated because you have to solve this W times P, which at least for now I don't know how to face it. So I had to do this. And the big problem, and maybe there is someone wondering that, is that since this heuristic approximation, the convergence time can't be, it's not guaranteed. I mean, you don't know, depending on the problem, it can converge faster, or it can converge, or it cannot even converge. So this is the problem of this algorithm. In my future work, I am pretty close from getting it. It's computing this matrix without using an heuristic algorithm. So this will be probably next year.
Great, so let's...
One question?
Okay, so let's thank the speaker for the last two talks. And our next speaker, which will be the final one of this session, which is the last session of the day before the posters, is Changsheng Hua, who was the previous session chair from Tsinghua University.
And Professor Law from the University of Hong Kong, and Professor Emily from Tsinghua University. So this is outline of this talk. We'll first explain what is a local broadcasting problem, and then I'll practice the models and related works. Then I'll summarize what are our conditions. Next, I will introduce our algorithms in more details. I will conclude this talk with some basic work. So in many network applications, we always require that all the network nodes need to connect the information from the nearby nodes. This comes to the loop broadcasting problem. More formally, given a set of nodes V and the local broadcasting range R, we define a region or the subway, which is the range around the node V. And the delta subways is the number of nodes in the boundary region. And the delta is the maximum value of all the delta. And in cross technologies called the network theory. And the local broadcast is to make each node or way broadcast a message to all its wake-up neighbors in the region D0. The local broadcasting problem is to complete a local broadcast in as few time slots as possible. Since in our wireless scenario, each node can only receive one message from a sender. So here, the network degree delta is a trivial low bound for our local broadcasting problem. This, in other literatures, this problem is also called the minimum latency picking scheduling problem. And the picking here is that each node wants to locally broadcast a packet to all its neighbors. So in case something for some papers. So the reason we study this local broadcasting problem is that it is a building block for many higher layer protocols, such as routing, synchronization, coordination, broadcasting, and reaching out protocols. We study this local broadcasting problem in the unstructured wireless networks model. The reason we study this unstructured wireless network model is that it accurately reflects the initially deployed wireless hop in the sensor networks. And in this unstructured wireless network model, we assume that nodes are placed arbitrarily on the plane. and there are no collision detection of collision. By nodes, collision detection means that nodes cannot distinguish collision from anything else. Is that if a node cannot receive a message, that's not know whether the sender did not send a message at all, or there is a collision. And we also assume that each node has very scarce knowledge about the network topology. The node doesn't know the number of neighbors, even the maximum number of neighbors. And however, in our algorithm, we do assume that the node has a polynomial estimate n of the number of nodes in the network. I think this is a reasonable estimation, since there have been lots of algorithms to estimate the number of nodes in the literature. And in our work, we also consider asynchronous sequences. And by this, we are include that first is nodes we wake up asynchronously, which means that once some node has started executing the algorithm, there may be some newly wake up node just started joining this algorithm. And this we are called some problem. And in our algorithm, we also assume that nodes have no access to a global clock. That means that nodes have to communicate asynchronously. And following on most work on this local broadcasting problem, we always assume clock-based interference model and protocol interference model. And in our work, we consider the geometric SIR model. So the SIR means that signal interference plus noise ratio. And the reason why we put is that a geometric SIR model is that we consider only geometric space. Particularly in our paper, we consider two-dimensional Euclidean plane. And in case some of you are not familiar with this SIR model, we are bringing more details. In the geometric SIR model, the message sent by a node U can be successfully received by the receiver wave if and only if this inequality holds. And in the left side of this inequality, the numerator P sub U or P sub W is the transmission power of the node. And the distance du width means the distance between two nodes U and W. Alpha is a Pascal exponent. It's not between 2 and 6. The beta is a higher implied threshold. Normally we assume that beta is larger than 1. And the n here is the ambient loss. In the denominator of the double side of this inequality, it means that in the interference experienced by the receiver wave caused by all simultaneously transmitting nodes in the network. So this is actually compared to different from the graph-based interference model or protocol interference model. And this aggregate interference brings a global constraint to our problem. This also causes some challenges of designing distributed algorithms. Since we are considering distributed algorithms and we assume a synchronous recap, we define our performance measure as follows. The first, the running time T sub wave of the node wave is defined below. First, small T sub wave means the time that the wave starts executing the algorithm, and the T sub wave star means the time that the wave quits the algorithm. The minus of these two values means the running time of a specific node. And the full running time of the algorithm is the maximum value of all the running time of the node. So if the nodes are synchronously wake up before starting the algorithm, this performance measure is equivalent to the minimum latency thickness scheduling problem. Now we are building some relation work for our problem. First of all, I will explain what is unstructured wireless network model. This model, as I just said before, can accurately reflect the initially deployed wireless networks. This model was first formally proposed by Fabian Kuhn, Thomas Bruder, and Robert Harper in Mobile Com 2004. And then there is also a similar model called the weak sensor model. This model was first proposed in Barra-Harton, Landers, and Ontario in ESA 2005. As I mentioned before, most of this kind of theoretical research consider only this graph-based interference model, the protocol model. For the geometric SI model, in recent years, starting from Thomas Bruder's IEEE 2006 paper, there is a surge of research around the geometric SI model. such as in many flagship conferences, such as Mobile Con, InfoCon, IPAP, SPA, we have frequently seen these papers that is studied under the geometric model. And even there's a dedicated workshop called WIWF, workshop on realistic models on algorithm for large networks. This year is the third year of this workshop. And however, a lot of studies focus on designing this centralized algorithm instead of more tactical descriptive algorithms. When it comes to our specific local broadcasting problem, there are only a few ways to consider designing distributed algorithms under the geometric SNR model. The first one, this is probably under the geometric SNR model given by Oda consumer program that covered in a Tom C 2008 paper. In this paper, the authors proposed to randomize distributed algorithms. These algorithms are divided in two parts. If the node flow the log data, that is another degree, they propose all the data log n time randomized distributed algorithm. If the node does not know the knowledge data, it is an unknown network model. It's a similar to unstructured network model. They propose randomized distributed algorithm which consume time all the data log n cube time complexity. In the InfoCon 2010 paper, Professor Wang Zhenjun and Wang Du, they proposed a deterministic centralized local broadcasting algorithm with a constant approximation ratio. Actually, in that paper, they don't call it local broadcasting, they consider it a linear scheduling problem. And in our last year's DCOSS paper, we also proposed two distributed algorithms under the unstructured one-to-one model. The first result is that the node has a collision detection ability. We can design a deterministic distributed algorithm of all the data log n times complexity. If we don't assume collision detection ability, we have designed a randomized distributed algorithm with time all of data log n squared. This is the only work distributed algorithm or randomized algorithm for local broadcasting with SNR model. In this paper, we first give a randomized distributed algorithm that completes the local broadcasting problem in time on the data log n plus log n squared. And for all that works with small constant data, this result outperforms the figure of our result, is our previous result, of data log n squared. And then we also derive a new lower bound, which is omega data plus log n for the local broadcasting problem, which improves the previous trigger omega data lower bound. And based on the upbound low bound, we can show that our distributed algorithm has an log n approximation ratio. Now let's put it more clearly why our unstructured network model and the geometric model brings more challenges for design efficient distributed algorithms. The first is a geometric model. And as you know, in the geometric model, if we want to finish this local broadcasting or the scheduling as fast as possible, we must allow more simultaneous transmissions. However, if there are more simultaneous transmissions, they will cause more aggregate interferences. Thus, the practice of the algorithm is hard to guarantee. And the third thing is that in the SNR model, we have global interference constraint, right? So this gives another challenge for designing distributed algorithms. And for synchronous wake up and synchronous communications, it will also cause some challenges for designing distributed algorithms. For example, if some node has executed the algorithm already, but some node are just waked up for the single wake up reason that we want to save energy. If the node does not need to wake up, just go to sleep. And if it's necessary, just make it wake up. And this will cause the network hard to design distributed algorithms. The third one is that there is no neighborhood information. We can't set each node transmission probability based on the network degree data, because there is a first in the Tom C 2008 paper, the authors, if the node network degree, they can easily set a probability transmission to guarantee an efficient randomized distributed local broadcasting problem algorithm. Next, in our algorithm, I will show how we solve these three challenges in more details. is a clustering-based strategy. By clustering, we mean that we first perform a leader election process. This leader election is performed by performing a distributed maximum independent set algorithm. This maximum independent set algorithm is also the original version is designed by Thomas McBurda in the square-based experience model. But we have last year's hypersensitive paper we have proved that by adapting the maximum independent set algorithm, we prove that this distributed maximum original distributed maximum independent set algorithm can also work under the geometric model. And then each inactive leader will just perform the broadcasting. And for the long leaders, for the local broadcasting, this job is responsible for the leaders, which means that the leader will coordinate with non-leaders to the broadcast. We are assigned non-overlapping time slot to all its non-leaders. So this is a basic idea of algorithm. And to guarantee our algorithm work correctly and also efficiently, we set different states and messages used for algorithm. We would have set different 3 states to coordinate those operations. The first state is called state D. The node in state D, they are leaders, such as the independent set node in the maximum independent set algorithm. The second state is called C, which means that the node in this state, they are non-leaders and they are competing the rights for local broadcasting. And the state E means that they are also non-leaders, but they are performing local broadcasting. You have gained the right of performing local broadcasting. And there are also set 3 different messages to coordinate these operations. The first message is called start compete. This message is used by the leaders. The leader will use this, send this message to his non-leaders to compete for the right of local broadcasting. The message request right is used by the non-leaders. The non-leader will use this message to report this ID to the leader. And the third message called grant is used by the leader. The leader will use this message to inform our non-leader to perform local broadcasting. So this is 3 states and 3 messages used for coordinating our distributed algorithm. This is a more detailed description of our algorithm. This is a little bit different from our paper because we cannot put all the details on this slide. And you can see that here, the last 3 lines, these are 3 states, right? This is no state D and no base state, no base state E. The first line is that because we consider a synchronous wake up, right? And each node we are perform the algorithm individually. So upon the wakes up, we first force this node wait for all the log n time slots. And in this time slots, if we receive the start compute message, which means that the node will go to the state C, non-leaders, they will consider to compute for the right of local broadcasting. And this leader is you, right? We can submit here. And if the node wait did not receive this message, it will be exactly the maximum independent set algorithm, which is developed by last year's hypersensitive. And in this maximum independent set algorithm, the node will, as I said before, the leader will perform local broadcasting algorithm directly. And if the ought to handle the newly wake up node, and if the node does not, on one hand it will perform local broadcasting, on the other hand it will also transmit a start compute message to its non-leaders to force its neighbors to newly wake up node to join state C. This is detail. We cannot make it clearly on this slide, but we can refer to our maximum set paper. And the node, if the node is in state P, and for all the log n time slots, we will transmit some message to the constant quantity. And for all the log n time slots, ground message. I will not go into the details. I just want to mention how our algorithm solved the 3 challenges we mentioned before, right? For the first challenge is a global SIM model, right? And the SI model, for the efficiency, we want more nodes to be scheduled at the same time, right? But if we are it's difficult to guarantee the correctness. And in order to solve this challenge, we did this, we did this, yeah. And we first we said we have devised a novel probability adjustment strategy. And firstly, originally this probability is very small. We did not mention in this slide. It's a very small value, and if the node, if the non-leader does not receive the ground message for it, then it will double its consistent probability. And here, it has received ground message that is not for this non-leader. So in this case, it will halve this consistent probability. So in this case, we can not only increase the simultaneous transmission, but also can, in appropriate time, can reduce the expected interference. For the second challenge, there is no neighborhood information, right? And for this information, we for no neighborhood, for the second concern is that we first, for the newly become node, right? We ought to deal with this problem. We first, for the node in CD, we will first consider the start impedance density, right? To force the node non-leaders to go into the CDC. This will solve the newly become node problem. And in the node in CE, we can use all log n times to transmit with constant probability. This constant probability will guarantee that all the nodes can finish the successful node broadcasting as quick as possible. And now we give the time complexity. And the time for distributed maximum set area we call consume time log n squared. And time for C in this three states either consider log n, log n, log n, log n squared. And put together the total time correctly, all the data log n, log n squared. And the no bound is that no bound, first of all, only the data is natural bound, right? Not to prove only the data plus log n no bound, only prove that there is no rule that any level mass calculator need only the log n times out from the probability 1 minus 1 of n. So this gives our strong middle bound, and this middle bound can prove our approximation is all log n. Now to conclude our work, in this table I give an improved upon strong middle bound for the broadcasting and structural lines in the works and the design model. And our algorithm has a log n approximation. For future work, the first thing is to design deterministic distributed algorithms. I think this is an important one because the normal just use some probability adjustment. The second one is to consider unreliable channels, for example, phosphate. This I think is a realistic model, right? This is the reason why the workshop this start 2011, well, people consider relay feeding, there are also DC feeding and alpha feeding models. And in our paper we can relax. How about the node does not level node? And in our paper we also consider uniform outcome. How about with our control? Thank you.
So that concludes this session. I guess if we have any questions, we can chat at the poster session. Thank you very much, Cheng Cheng. That was an excellent talk. And now I'll hand it over to Luis Almeida for posters, work in progress, demos.
Thank you very much. So as I told you before, so we will do a quick handover, and we will just right away start with a short and brief presentations. And we are going to start with the first one, which is the work in progress paper that we have. And this is actually a mixed session, so it's a mixture of 3 sessions. So it's the work in progress, poster session, and demo session. And the work in progress, we have only 1. The posters, we have several, and demos, we have 2. But all together, I think it's a nice set. And so we invite you to stay. The idea of these short presentations is just to give you a quick idea about what the works are about, and somehow to motivate you to come and meet the authors by the posters. And the posters are right at the precise, let's say, space and moment in time to wait for the bus for the dinner. So while you wait for the bus, instead of being annoyed somewhere, you have the chance to chat with the authors, right, of the posters and talk to them about their work. So thank you very much, Richard. So we'll start with this work in progress about resource-aware fault localization in large sensor networks.
Okay, thank you. I was supposed to have 8 minutes, but I will hurry up to let others also talk a little bit. So maybe I skip some details, but I also have a poster outside, so we can talk about it later. So